All right. Looks like we're straight up noon and East Coast time. Let's get this thing kicked off here. Hi, everybody. Really appreciate your sitting in with us today. I know it's a super busy time for most people, and your time is valuable to you and to us. My name is Ed Creedon. I'm a senior project manager with AST Environmental. I'll be hosting today's webinar, and we'll be introducing our speaker here in just a moment. First, I'd just like to encourage everyone with us today to participate in this event by posting your questions in the chat box as we go along. I'm sorry, we do have a Q&A box down there. You can use the Q&A box, not the chat box, and that's a little more private there for you. So we'll save some time at the end and get to those questions. And if we don't have time during our allotment here to get to your question, we'll reach out to you directly very soon. So I'd like to take just a few moments to introduce you to AST. For those of you not yet familiar with us, AST is a member of the RPI group, and we're headquartered just outside of Lexington, Kentucky and Midway, Kentucky. We have several offices located around the US, including where I sit here in Kansas City. We also have people in Denver, Colorado, the Philadelphia area, Harrisonburg, Virginia, and Springboro, Ohio. Our team is made up of remediation, chemical and civil engineers, geologists, environmental scientists, and environmental technicians. And a lot of us, if not most of us, have spent at least a portion of our professional lives working as environmental consultants prior to joining AST. We're all very much we very much enjoy supporting your efforts to get sites closed safely and efficiently using a variety of in situ remediation technologies. I mentioned the RPI group. This is a group that's made up of Remediation Products, Inc., the developer of the activated carbon-based technologies known as BOS 100, BOS 200, 200 plus, and CAT 100. And other members of the RPI group include authorized installers of these technologies located in the US, Canada, Australia, and Northern Europe. AST is also an authorized installer, and we're the national and international distributor of all of the RPI technologies. And we're also responsible for in situ design plans and quality control of the RPI group field services. If you haven't seen any of our recent announcements pertaining to our new services for PFAS impacted sites, I'm excited to tell you we've entered into an exclusive agreement with Setco. Setco is a mineral technologies company, and this agreement allows us to perform in situ remedial injections of Setco's proprietary FluoroSorb adsorbent technology. And prior to now, that material was being emplaced in a variety of different methods, but it was not being injected. So like the activated carbon-based technologies, this material, the FluoroSorb adsorbent, is a solid material, and it's applied as a slurry through direct injection by AST. It's a really great fit for us. We've spent the last couple of decades developing and refining slurry injection processes into overburden, transition zones, and fractured bedrock. And we can provide those injection services, by the way, for a variety of in situ amendments. So please don't hesitate to reach out to us for support on any of your injection projects. Okay, I better get to Bill, get him on the stage here before I use up too much of his time. Bill is a professional geologist, Bill Brab. He serves as a senior remediation geologist for AST. He's been with the company for many years, and he is the go-to guy for many of our clients looking for innovative ways to remediate their sites in complex geological settings. As I believe most of us here today know, successful in situ remediation is heavily reliant on having a comprehensive understanding of where and how much contaminant mass is present at a site, and just as importantly, making direct contact with that contaminant mass through effective emplacement processes. And Bill's talk is going to address all of these issues. So please sit back and enjoy, and don't forget to fire off some questions. I'll be back later to go through your questions with Bill. All right, Bill, did I save you enough time, I hope?
Sounds like you did, Ed. Can you hear me okay?
I've got you. Take it away.
Wonderful. Thank you, Ed. As Ed said, thank you everyone for attending the call today. Everybody's schedules are quite valuable, and their time is important. And we definitely appreciate everybody who takes the time to sit in on any of our presentations and hear what we're working on. As Ed introduced, again, my name is Bill Brown. I'm located here at our headquarters in Midway, Kentucky, serving as a senior remediation geologist. And I'm going to talk about a site here that does involve, as Ed had said, looking at a petroleum hydrocarbon site through the various stages of investigation and remediation and post remediation evaluation. So with that, we'll move forward and stair step through all of these slides that I'm going to show you today. And of course, I wouldn't want to move any farther forward without acknowledging all the folks that were involved and a part of the collaboration on this particular facility that I'm going to talk about today. I want to thank the regulatory body of the Tennessee Department of Environment and Conservation, Division of Underground Storage Tanks, specifically Doug Cantrell, who is situated in the Knoxville office, who's been a key champion with working with us in the past. So definitely a big shout out and thanks to Doug. Want to thank our client, SEMS of Tennessee, Roger Paulson specifically, who is the certified contractor that oversees the operations at this particular facility, as well as the other facilities that we work on with SEMS. And then finally, I want to thank Dakota Technologies Company, specifically looking at Kevin Vandervoos, David Hiker, formerly of Dakota, and Randy St. Germain for their involvement in this project as well. So as we move forward into talking about this facility, I always like to start with our case studies with a historical conceptual site model, or CSM, when it comes across my inbox or my desk for evaluation. So with any project that we become involved in, there's a request for all the historical information related to the site so that we can look at what's been done historically and have a broad picture of the activities of the facility and what is essentially the status of the facility as of the moment of review. So we have our site map here on the left-hand side, former tank hold located to the south, retail gas station, as we can see right here with the canopy. And looking at the previous investigation as well as remedial efforts at the site, we have some monitoring wells located here by the blue points, as well as some recovery wells related to a corrective action system, which was acting as a dual phase extraction system to treat mixed media at the facility out of these recovery wells located in red. What I also want to talk about is this general area of interest that we had located at the facility, extending from the northern part of the site, adjacent to 3rd Avenue and parallel to Main Street, to the south, extending to just south of RW1 and coming across the front side of the on-site building, was on the order of around 8,100 to 8,130 square feet. Historical groundwater concentrations at the facility ranged anywhere from 5 milligrams per liter to 25 milligrams per liter in the near time adjacent to looking at this facility and this particular conceptual model at the time. Again, talking about that dual phase extraction system located at the site had mitigated the mobile and migrating LNAPL while the system was operational at the facility. And that LNAPL in the recovery and monitoring wells at the site ranged anywhere from 1 foot to 3 foot thick historically as it was measured at the facility. One of the data gaps identified during the conceptual site model was the amount of soil data available for looking at sorbed phase contamination. All of these samples to date at the time in 2018 were restricted to the unsaturated zone of the vertical column of interest. And the actual VOC's testing was restricted to the contaminants of concern related to the regulatory program, looking specifically only at VTEX plus MTBE and naphthalene. And when looking at LNAPL sites, we also are very interested in the total mass fraction of analysis to be performed. And this particular site had not had that analysis performed on the soil samples to date. So no TPH data was present. And one note that's also of interest is that this is not the only facility with USTs in the area. There were numerous identified orphan tanks within approximately 300 foot of this facility that were of interest to note as well during the historical assessment and investigations out here. So as part of the data gap analysis filling, we wanted to recommend the first stage of the assessment was to do a remedial design characterization, or RDC for short, as we're going to identify it from here on out, which was conducted in 2018 as well, late summer. And this, here's our area of interest identified by the red dotted line, as well as our RDC sample locations identified as the orange dots proposed on the map here. We had 7 continuous soil borings proposed that were completed during this time frame. Samples were collected continuously from 10 foot below grade to 30 foot below grade. And that analysis at the laboratory of every 2 foot below grade was completed using VOC's 8260V method, as well as looking at the PDPH, the total mass fraction analysis that would look at that component as well, to look at everything within that hydrocarbon chain. In addition to the soil borings at each of those locations where we pulled soil cores and samples from, small diameter 3/4 inch piezometers were installed at each of those soil borings as well prior to abandonment. Those were also analyzed for both VOCs and PDPH, but then in addition, we looked at anions using method 300.1 and dissolved gases using RSK 175 to establish a baseline for this data set prior to doing any sort of augmentation or follow-up remediation, as is typical for any of the sites that we become involved in. In addition to that, we also looked at the existing monitoring and recovery well network, looking at the same sampling suite that was performed on the temporary assessment wells that were installed in the soil borings prior to abandonment. So a lot of text here, but we'll walk through it fairly smoothly, hopefully. So looking at the findings and then the eventual remedial design that came out of this RDC that was performed. So a preliminary design was provided to the client for evaluation prior to conducting the RDC. And that design was, to be noted, was based upon the groundwater data only that was available in the historical conceptual site model. Because the soil from the unsaturated zone only was not in play with this particular investigation, because we're treating saturated zones only. And both sets of data, the soil itself and the groundwater, was limited to that VTEX, NPD, and naphthalene only. And it's also noted that the groundwater was taken from longer screen intervals that extended anywhere from 20 foot length to 25 foot length below grade. So we're taking a large composite sample across a fairly long interval. And so fairly conservative estimates and numbers within that preliminary design were provided on the front end. But once we look at the RDC plus the conceptual site model update, some important key factors came into play that were of note that drastically changed this preliminary design to an interim corrective action. There was significant saturated soil mass identified from 15 foot to 20 foot below grade. And that concentration was anywhere from 10 times CSAT in the 2,500 to 3,000 ppm range of PDPH, as high as 14,900 ppm of PDPH in one particular sample. So some pretty significant mass located at the site, concentrated in a very narrow band located at the facility. There was also some shallow unsaturated source soil mass located adjacent to the pump island and canopy that was also identified here. And based on this data from the soil borings and looking at the lithologic logs, the impacts to groundwater were likely being attributed to an interval that was shallower versus the total length of the screened interval that was installed in the wells and monitoring wells and recoveries at the site. So as following up with this update and looking at this data, an interim remedial injection design was provided that had a segregated or differentiated zone of treatment. And so if we look at the shallow zone design basis, this was based upon the saturated soil TVPH concentrations that I've noted above in the third bullet or the first bullet under the RDC and CSM. Whereas the deep zone basis was based on groundwater concentration, benzene concentrations in the existing wells. And this is important to note because even though the soil data did not indicate that there was mass in that deeper zone, we do have a protection of groundwater consideration to any sort of mass that may migrate vertically, but also we have access points in the form of recovery and monitoring wells that have penetrated that zone with a potential sink of concentrated groundwater with mass in it that's in contact with that lower interval. So we want to make sure that we cover that zone as well, using those groundwater concentrations as the basis for that treatment. And I've also note that's important with this particular interim remedial injection design that's about to occur. That zone of high concentration that I note above with the 14,900 ppm of TVPH, a pilot scale second injection was initiated at this site to address that shallow mass located in Area E during the same mobilization. So this is important here to try and get additional treatment platform and terminal electron acceptors in the ground in order to provide a more timely time frame to reach site closure and manage risk in that area. So graphical representation with detail of the actual injection design itself for this interim corrective action. At this particular site, we deployed this in November of 2018, extending into December 2018, utilizing the BOS 200 technology. This is prior to 200 plus coming on the market. And for those of you that aren't familiar with it, BOS 200 is a powdered activated carbon, and we mix terminal electron acceptors in the form of sulfate and nitrate. With that powdered activated carbon, we also add micro and macronutrients and a consortium of facultative bacteria that are inoculated in that mixture prior to injection. So all of these materials are mixed in the mix tank prior to injection. Because of the mass at the site and the concerns about depletion of terminal electron acceptors, we added supplemental gypsum to provide a slow release long-term form of dissolved sulfate. We also added our bacteria concentrate, again, looking at that treatment area of interest of roughly 8,130 square feet. On a 7.5 foot grid spacing, this came out to about 168 injection points. Again, targeting that shallow interval from 15 to 20 foot with the deep interval from 20 feet to 30 foot. And then looking at area E, this is this orange area up here around RW5 and MW7. That's that area of that significantly high mass. We started in this area, worked south, and then came back north at the end of the injection prior to demobilization and performed essentially a second injection event in that area where we offset the points and created a new grid and re-injected in that area to get additional treatment platform in that zone to provide additional risk management in that area. So we're going to fast forward now. After the interim corrective action, we do cradle to grave performance monitoring of sites when we have the opportunity to do so. It's recommended as part of our plan. And so quarterly following the injection event at this facility, groundwater samples were collected from the existing monitoring and recovery well network to look at and gauge performance over time following this injection event. And so we're going to look at a snapshot approximately 17 months post-injection through June 2020. And essentially what we're doing here is at this point in time, the regulatory body, the client, and AST are evaluating and determining what sort of future actions may be present at the facility and what's going on out here. And so again, just to re-highlight and talk about what the findings were during the RDC, the significant mass identified during that period had one of two options occurring that needed to be considered for a path moving forward. Based upon raw modeling calculations, multiple injection events would have been required in order to reach cleanup within a more expedited, timely fashion. However, cost feasibility and physical feasibility of being able to implement that much remediation chemistry came into play that prevented that from occurring. And so looking at this interim plan that was implemented as discussed in the previous couple of slides, that remedial goal based on modeling was anywhere from 5 to 6 year period post injection if everything remained constant, thermal electron acceptors were not depleted, et cetera. So modeling said that we're looking at, even with all of this, a 5 to 6 year period. So looking at bullet number 2 and working our way down, we've kind of got a baseline here of concentrations, and I'll kind of walk you through what all this means. So looking at the original status of the wells prior to, or excuse me, during the RDC, we have, let's just look at MW5, for instance. This first number of 5.46 is the benzene concentration in parts per million, and our TDPH concentration in parts per million. And that nomenclature is propagated for the rest of the points here, as well as what's below. So fast forward now to the sampling event in June 2020. You can see those values posted here. I won't read through and call out each and every one of those for you. You can see those on your screen. But what I want to call out here that's of interest to talk about, that initially just looking at the groundwater data that's important, is the relationship of the concentration of the TDPH versus the benzene that we're seeing. And so we can see percent reductions noted in this final section down below. And we can see highlighted values at MW5, RW5, and RW1. And the interesting piece of data to note here that we see in this analytical that came out of this time period and subsequent time period is that when the concentration of the TDPH is below 50% or close to 50%, we have a tipping point of the relationship to the reduction or stability of benzene in groundwater as well. So we're just going to take a look at MW5 again, for instance. So MW5 having a 34% reduction, which is below that threshold of 50%. The baseline during the RDC was 5.46. The current concentration in 2020 was 4.87 ppm. We can see that those numbers are relatively similar. So what we see here is that when the TDPH concentration percent reduction is below 50%, we can see that that number of benzene stays relatively stable. And this makes sense because it's one of the more recalcitrant compounds, and it's less likely to degrade than some of the other compounds we may see within that VTEX MTBE naphthalene stream. However, if we get into these zones, like if we just, for instance, look at MW14, for instance, we can see more marked reductions in benzene. So we've got a 99% reduction of TDPH in these two sampling events, and we can see a more significant, call it close to 50% reduction of benzene within that particular zone. So this is important to note. We're going to kind of highlight on this piece of information here as we move forward through the data and the remaining portion of this presentation. So following the evaluation of the groundwater data, it was elected to come out and perform a UBOS survey in January 2021 and look at the presence of any remaining LNAFL at the facility that could be detected with the direct measurement tools of the UBOS measurement here. And just to kind of highlight and briefly describe this information here as presented in Dakota's report, 35 borings were initiated at the site, UBOS borings. And what was interesting to note here was Randy St. Germain with Dakota had done some very extensive and interesting studies looking at the BOS 200 technology at the bench level before going out in the field and looking at this in subsurface in situ conditions. And what they found, or what he found specifically between the bench and the subsurface laboratory, so to speak, is that the BOS 200, when detected, suppresses the fluorescence of the PAHs in the subsurface. And it also can show a typical shortening of the lifetime of that fluorescence and what would be considered, or it's been called, blue shifting of that. And we can see that called out here by the arrows and by this particular detection in lift number 21. Anybody that's interested in this, I know Randy has presented this at a couple of conferences already, and you're more than welcome to reach out to him directly and get more information about this particular result and finding that he determined here. One other piece of note that's of interest here that is also important to consider is that this UVOS survey was considered an afterthought, so to speak, as part of the investigation. So it came in as being assessed after the post-injection. So unfortunately, in this particular case, we don't have a baseline to look at and compare prior to augmentation, which again is important, and we'll come into that a little bit later when I kind of wrap this talk up, because there's an interesting result from that. So as part of the follow-up to that UVOS survey, ASP had started utilizing a quantitative high-resolution site characterization program, which is an expansion of the RDC program, and we deployed this at the site in June 2021. And this sampling plan took the information from the UVOS survey, the historical RDC, and the 2018 injection into consideration in parallel with the post-injection groundwater performance data. This plan consisted of 18 soil borings across the site, that each boring had detailed lithologic logging across the entire vertical length of that borehole. And that plan included, of those 18 soil borings, 7 of those borings were resamples directly adjacent to the 2018 soil borings for the purpose of apples to apples comparison of pre versus post soil sampling at the site. 2 soil borings were also advanced, soil boring 8 and 9, adjacent to the existing UST basin located here at the site, for the purpose of looking at unsaturated soil profiling for the potential of the excavation and disposal at a later time. All of this data was compiled into a 2-dimensional and 3-dimensional modeling program in order to look at that data for visualization and interpretation. And finally, the last piece of information that was assessed as part of this qHRSC was looking at a kinetic rate of decay to look at a comparison of soil samples or soil analytical data prior to injection versus at the current sampling period in June 2021. So here's some imagery of that 3-dimensional modeling on your left-hand side, looking at soil benzene isosurfaces with 500 ppb concentration in the bluish purple color, 5 ppm in the greenish color, and 10 ppm in the reddish color located here. And then similarly, we're looking at that soil TDPH at the bottom here at 500, 2500, and 5000 ppm respectively in the same color scheme noted above. So what was interesting to look at with this data, looking at as part of this modeling and part of this assessment, was to determine a kinetic rate of decay at the facility. And so this data utilized the comparison of the 2018 RDC data versus the 2021 qHRSC RDC soil resamples. So specifically, as I've noted at the sub bullet down below, looking specifically at the points that we can correlate and match up to prior to injection versus post injection, that being soil borings 1 through soil boring 7. And what was interesting to note here that came out of this particular calculation and assessment based on the data alone is that looking at the soil mass in those soil resamples, we had an approximate 57% reduction of the total mass at the facility looking at those samples during the time period. And if we look at that number and we look at the time frame and we back into the original assessment or the original assumptions in the modeling that we looked at during the post RDC, that matches parallel with and falls fairly close to the estimated time frame following the 2018 injection, as was predicted in the original interim remediation plan. So some interesting matching up of numbers here that was quite interesting to see. So it was elected to at the time, following this qHRSC program, to expedite site closure or to try and move things along a little bit quicker. And so this was completed in early 2022 in March. So we're looking at just over a year since implementation at the time of this talk. And so at this particular time, BOS 200 Plus is on the market, which was deployed at the facility at the areas shown here. And that consists of, just like the BOS 200 before, as the base, we've got the powdered carbon, activated carbon with the TEAs, the nutrients, and the consortium of facultative bacteria. But we now have added an additional string of bacteria that can provide essentially a breakdown of the complex carbohydrates and carbon at the site to provide additional sugars and electrons at the site to be able to bolster a more robust microbial population. We've also added, in addition to the slow release gypsum noted below, we've also added a highly soluble form of sulfate in the form of magnesium sulfate, or generically Epsom salt. The electron donor comes to us in the form of a food grade starch, cornstarch, and then we've added additional vitamin nutrients in the form of yeast extract. This particular area of treatment and investigation or remediation was about 6,700 square foot. We've gone to a tighter injection grid to enhance distribution and contact with the subsurface, which totaled approximately 188 injection points. But now we've come back in based upon the data that was found, and targeting and narrowing in on that narrow interval of 16 to 22 feet that was identified specifically during the qHRSC as being the most prevalent zone of high impacts and sword bats contributing to the groundwater problem of the facility within the saturated zone. So now we want to talk a little bit about kind of how the site is performing since the implementation of the BOS 200 Plus injection. So we've continued with the groundwater post-performance monitoring quarterly since the injection was completed. But one of the questions that came into play was trying to interpret the trends over time and how it relates to the performance at the facility. And so we looked at performing a Mann-Kendall statistical analysis of the groundwater facility, looking at the groundwater beginning with the sampling event prior to injection during the RDC, all the way up through the last sampling event, which was completed in November of 2022. So looking at groundwater data and the relative trend and slope of that trend with time at this facility at these respective monitoring wells. And so what we've plotted here is we've plotted the send slope, or what is called the S value in the Mann-Kendall analysis. And what this slope is telling us is that the value of that slope, whether if it's negative, you're showing a decreasing trend in the data over time. If it's positive, you're showing either a flat or an increasing trend. And so what we see here that's important to note is that the majority of the site is showing a decreasing trend, negative values down here in the greens and blues, flat being the yellow. And then we have zones that are stable or increasing in the reds and oranges, right? So what we have here that's of interest to note that I'm calling out here, looking at the benzene and the TBPH, is that this problem area to the south near RW1 and NW4 is of interest because what we've got going on here is we've got that zone of shallow unsaturated mass and the UST system that still remains in play at the facility that may have some corrective action in the near future. And so we've got a continued source that may be fueling groundwater concentrations in this area. And the data is a lot more erratic and chaotic in this area, which is showing this positive result that we're seeing in those particular slope values that are determined in this MK analysis. What's also interesting to note here is that if you look at the similar geometry of the TBPH on the right versus benzene on the left, is that you can see that in areas like specifically MW7, where you have a decreasing trend in TBPH, we may be getting ahead of some degradation here, where if you look at the benzene, we're seeing a more stable flat trend that is indicated by the color within this particular zone. So following again in parallel with some of this data that I mentioned earlier about your percent reduction of PDPH within the groundwater being a reflection of what you can predict and you can see in that speciated data, specifically benzene in the groundwater at a specific given location over time. And one of the final things we're going to wrap up with is looking at microbial analysis of the microbial population at the facility. And so Ed Winter had given a talk on this particular topic last week. I invite you to either watch his presentation when it becomes available online and or reach out to him directly with any more pointed, detailed questions that may come into play as you look at this data and try and interpret this slide. So it's a busy slide, a little bit difficult to follow, but I'll do my best to walk you through here. So we've got 4 monitoring wells that we're looking at here, and we had to basically pick a single well to kind of call the basis for assessment, which Ed picked as that monitoring well 14 here. And so then all the microbes that are within detection within that zone with a cutoff of around 1.0, I think is what he used as his kind of cutoff of percent abundance within this particular sample noted at the bottom. So it's sorting in abundance with a decreasing value going from top to bottom. Monitoring well 5 located at the center of the site, monitoring well 7 to the north, and RW3 located in the center of the site near monitoring well 15. And just wanted to call out here, just going to talk briefly and try and identify some of these important actors that are in here. Looking at Perlucida here at the very top, we can see has the highest abundance in 2 of these samples here. And what's important to note about these 2 is that, or about this particular microbe, is that it uses CO2 and acetate as electron donors and nitrogen as a receptor. But what's interesting to note here, or that's important to note about this particular microbe, is that it's extensive across the entire site, and it is in both the impacted and unimpacted samples. So this is your background species that is the dominant form out here. But then the next form that's very interesting to see, or that is present at the site, is Smithella, which is has been known and shown to be an alkane degrader, which includes the gasoline constituents. So we can see that in relative abundance in the majority of the samples as the second most abundant out here is present within the 4 samples that we're showing as well. The stick figures that we've got notated on the far right-hand side here, these are your petroleum degraders that are documented in the publication. But what we want to really take from this data, if we just look at it from, kind of sitting back in our chair and looking at all this information, is that the data that we see in these samples is consistent with the published literature and what you would expect to see at a typical petroleum site with biodegradation occurring. And I want to further add, just if we look at the specific microbes that are present here, these known petroleum degraders and the degraders that are the microbes that are present fall within the zone of the microbes and the reducing zone that we're augmenting and that we're creating at this facility based upon the technology deployed. We have sulfate reduction, we have fermentation, and we have methanogenesis. And so all of these are present and in relative abundance. And then the final note to note about this, and Ed and I talked with this before the call, is that, if you look at the data, Smithella, and if you compare all of these microbes as being a basketball team or some sort of specialty team, Smithella would be your key star player, right? So it's well known. It's going to take care of everything. It's going to do the bulk of the heavy lifting. But to be an accurate and effective team, you need to have a support team or support players. And so all of this diversity and this robustness of these other populations present. I mean, 7.8 of the sulfobulbus. I mean, that's a pretty significant number right there. Having that relative abundance allows your team to be much more effective and be able to handle whatever competition may be coming its way. So a little sporting sports reference in there for everybody. So as we kind of wrap up this talk here, just something that I want to close with and share with you is as we talked about before with the qHRSC program, we saw a relative percent reduction of total mass within saturated soil of approximately 57% as of the sampling event in 2021. I'd love to get some more soil data from here in the coming months or years to look at where we stand after the BOS 200 event, but we'll see how things go. Looking at the Mann-Kendall S-curve plot or S-slope plot, trend shows a favorable reduction in groundwater concentration across the site, both between PDPH and benzene. And we can plot that for any of the other constituents that are being measured. If we look at it as a whole, we see a very positive trend in the decreasing direction across the entire site. So looking also, I mentioned the blue shift in the Dakota survey earlier and how that would come into play later. That's quite interesting to see. Dakota did conduct a survey at a similar site nearby in Tennessee where there was a pre and post UVO survey conducted. And what was interesting to see there, and I can't remember the number offhand, I don't have the study in front of me, but what it shows that's very interesting related to this particular data is that the percent reduction in the NAPL percent RE that was highlighted in that report that's quite interesting is that we see a similar, call it 57% reduction in the percent RE mass pre versus post injection at that facility. So we're seeing a similar time frame of injection versus follow-up survey of the UVOS data that shows that similar time frame and similar reduction in that piece of data. And then finally, two other pieces of information that could be contributing and need to be assessed as part of a follow-up discussion with all the stakeholders involved is that the unsaturated or unaddressed shallow unsaturated soil mass that remains adjacent to the source or sources, being the UST basin and Pump Island canopy, still remains at the site. We do have remedy in place to protect groundwater below, but as long as we have a source that continues to pour into that, it's going to dictate the time to closure that could extend or delay that in some way, shape, or form. And then finally, going back to that discussion of unaddressed mass, there is a significant amount of inaccessible saturated mass that was identified or alluded to, so to speak, during the qHRSC program that looks to be up under the roadway, which is off limits for any sort of work. So looking at groundwater flow direction and things like that with time, we could have a continued source that could be bleeding into the area as well, coming in from that main street to the west. That could be a contributor as well to what we're seeing in some of these areas that are slower to perform than would be ideal. So with that, we look like we're hopefully still on time with wrapping up this and allowing time for question and answer. Definitely want to thank everybody for taking the time to hear my presentation today. My contact info, if you want to reach out to me directly, is at the bottom of the page. And keep an eye on your inbox. You'll get a notice that this is online at some point, I believe. Otherwise, you can just go to our website here, looking at the subsection webinars, and you can see all of our historical webinars put together to date, as well as any future ones that may be coming into play and presented to you folks at a future time. So with that, I will wrap up my portion of the discussion, transition back to Ed, who's been monitoring the question and answer section, and I will cover anything that maybe I didn't go over in detail or any follow-up questions that may come into play here.
All right. Great job, Bill.
Thank you.
Got a few questions stacking up here, and I encourage you folks to throw some more in as we go. If you get inspired based on what we're talking about, we definitely have plenty of time. I'll skip ahead to one here that's related to one of your last slides there. So why don't you also treat the contaminants above the smear zone in that unsaturated zone?
Yeah, it's an excellent question. So looking at the technology that we deployed, so the BOS 200, BOS 200 plus technology is a solid particle that's been placed in the formation, and it relies on some mechanism of mass transport. And so what we've seen historically is that with unsaturated situations, you're dealing particularly with vapor transport. And when you're looking at vapor transport, but then also combined with the concentrations and mass that's present at the site, first of all, the vapor transport is very slow, but it's also, when you account for that time frame plus the amount of mass present, time-wise, it's not feasible to deploy this technology specifically in an unsaturated setting. And especially if that mass is directly accessible to more conventional means of methods like excavation, it makes sense to remove that material directly and eliminate that source altogether.
Okay, very good. Okay, and then here's one regarding the microbial aspects here. If we know that we already have petroleum degraders at a site, do you still need to add your bacteria to the product before injecting?
It's a good question. So it's beneficial to add the bacteria to the technology prior to injection for a couple of reasons. First, the background population or the background microbes may not be robust enough or in sufficient population to be efficient, but there's also a lag period of being able to bolster that population in situ. The carbon, the activated carbon with the trap and treat technologies provides quite a few things. Ed Winter, again, I mentioned him a moment ago, talking about the microbial side of things, has done a presentation in a study looking at microbial growth on the carbon substrate itself. And so the carbon provides protection for the microbes, especially in situations of high concentration and LNAPL being present at the facility. You know, just throwing a bunch of bugs in the ground or relying on bugs in the subsurface, they have to deal with toxicity issues. But it also provides a medium for that population to grow and to proliferate. And so again, Ed talks about this. There's a well-known concept of diet that allows for direct interspecies electron transfer that is enhanced by the actual presence of the activated carbon. So there's multiple benefits of coupling these two pieces of technology together in a common mix tank prior to deploying it on a contaminated site. Okay,
very good. I have a question here about the CSAT values. What value or reference do you use for CSAT? And does this apply to TVPH data? And does it vary according to LNAPL source type?
Yeah, excellent questions. So yeah, there's several questions in that question. So the CSAT value is referenced in IPRC and back referencing into an ASTM document, or excuse me, API document. And for gasoline in this soil type, you're looking at a concentration of PPH gasoline range organic somewhere in the range of 250 to 500 ppm, depending on which soil type you're looking at. Now, that's looking at pure soils with no heterogeneity to it. So we typically like to look at a 250 range on this soil type as the TVPH value. TVPH, I didn't explain earlier, and that's a good question. So TVPH stands for total volatile petroleum hydrocarbons. And this is, think of it as an extended range TPH grow. It goes slightly higher on the C range and slightly lower on the C range than that TPH grow bracket. So we're capturing some of the lighter and heavier compounds on either side of it. And I think that answers all the questions. Did I miss one?
How it varies according to LNAPL source type, that, you know,
yes.
Diesel. Yeah.
Yes. So yeah, if you get out of gasoline, you've got some varied levels for TPH grow, and then your heavier, you know, oil range type materials. And those values are in fact published in the API document.
Okay. All right, a question about the blue shifting in UVOST. They're essentially asking what was learned by this blue shifting phenomenon.
Okay, yes. So the blue shifting, and again, reach out to Randy St. Germain, please, because he's the expert and had done this study. I don't want to get too far into the interpretation without his say or weigh in on it. But what I understand from his sharing of the data with us and what he's presented before is that you're basically seeing the presence of where the BOS 200 product is located in the subsurface. So it has some effect on the subsurface and on the detection of that percent RE from that sapphire window. And it doesn't, at least at the time that he presented it to us historically, he couldn't attribute that to a specific hydrocarbon compound. And so it was very unique to this technology and its emplacement within a specific geologic media.
Yeah, okay. Let's see. Is this appropriate for use in the presence of domestic wells? Basically the BOS 200 product, including breakdown products and microbial load.
It's a good question. So most domestic water supply wells that we come into play with a lot of these facilities are either vertically screened or horizontal distance spatially beyond the area of treatment. So the technology itself, once in place in the formation, does not move. It stays where you put it. And so the material itself will not migrate into the domestic use well vertically or horizontally after the injection has stopped. And so the only other components that you may consider that are soluble and mobile, so to speak, would be any sort of solute coming off of that terminal electron acceptor or even your microbes. But the microbes tend to populate and adhere to the carbon. They really don't want to leave and venture. You consider them. They don't want to venture out and kind of go exploring. They want to stay nice and cozy in their apartment complex. And then your terminal electron acceptors, they don't migrate very far from the point of injection. They tend to be consumed within the area of injection or dissipate quite quickly within the formation adjacent to the injection area.
Okay. Couple questions here, very related. Let me start with maybe the simpler version here. How long will the activated carbon be effective at a site where L-NAPL is present?
Mm-hmm. Okay. Well, so the activated carbon, again, it's in place in the formation. It doesn't break down. It doesn't degrade. And it essentially becomes part of the aquifer matrix. And so I think there's two parts to that question. So the effectiveness of the carbon, it has to be coupled with the technology itself, right? So we're not just putting activated carbon in the formation. So in that case, if you were just putting activated carbon in the formation, the effectiveness would be dictated by its saturation limit that's available to hold mass on that carbon. So because we're putting in a treat mechanism, hence the trap and treat products, we are allowing for regeneration of that carbon over time in situ. And so to kind of expand on that question of effectiveness over time, that effectiveness is driven by the amount of terminal electron acceptors present and available to that microbial population to utilize as part of that degradation process. So the only issue you've got to be concerned about is having enough terminal electron acceptor to sustain that reaction over time. Otherwise, you force or you face the risk of having a stall later down the road. But as you can see from some of the designs that were implemented out here, we've tried to account for that loss of TEA over time and tried to bolster that with additional materials to further augment and sustain that reaction with time. And that's why we look at that baseline anion and dissolved gas data, and then also carry that analysis through post-injection performance monitoring, is we're monitoring not only the degradation and reductions in COCs, we're also looking at those other constituents to look at the interplay of that usage of those materials plus the reaction with the contaminants present.
Right, okay, and it ties to another question that was asking, is the amount of activated carbon installed sufficient to completely absorb all the contamination on the site? And I think you addressed that pretty well, that that's not the goal.
No,
Although it's certainly part of the design process, it's not the goal to completely absorb the entire mass because of that treatment mechanism you're describing.
Right, and that comes down to a cost feasibility, but then also a practical installation feasibility assessment, right? We can look at, in some cases of these high mass sites, we can't physically put enough carbon in the ground. We just can't. We can't inject it. We can't occupy that zone of contamination with enough carbon to address that mass. And so when you're looking at that mass balance load, you've got significantly less carbon than you can physically put in the ground or address that contaminant mass over time. Plus, it's expensive. Cost-wise, it doesn't make sense to do that. When you have a treatment mechanism in place, you can allow the natural microcosm that comes with that implementation, with that inoculation. You can allow that to naturally or augmented degradation occur from that process of the treat.
Okay. So a question about the remedial design characterization process that you described. So do you help your clients develop the technical approach for a remedial design characterization to make sure that you get what you need for your design plan?
Absolutely. Some really great questions out of this talk here. So it's a collaborative effort. So we want to bring all the players to the table. We don't want to operate inside of a box. Both the regulatory body and the client consultant in this case have worked extensively on these sites, and they know quite a bit about these facilities more than we do when it comes across for our assessment and evaluation. And we like to come to the table and work on that together and try and come up with a plan. And then when we deploy it in the field, we typically want to be standing side by side at the sample table, looking at the drill rig and doing what we're doing.
Okay. And a couple questions here about installation of these products. Are you concerned when you're injecting with high energy? Are you concerned with mobilizing LNAPL or even dissolved contaminants to new areas when you do these injections?
Yeah, good question there too. And it kind of goes back to the domestic water well question. So relatively speaking, when you look at the amounts being installed and the fluid volumes that we use to make the slurry and to essentially act as a carrier agent for the solid particle we're installing, it's very small volumes in relative comparison to the aquifer matrix and the liquid volumes present within the pore matrix of that aquifer matrix. So we're putting in very small shots across a dense zone. So we're just putting enough energy and enough fluid in to distribute locally within the point of injection. So in all the years that we've done this work, we have not seen mobilization and pushing, so to speak, of contamination or LNAPL beyond our area of treatment.
Okay, and then another installation type of question here. In the intro, it was mentioned that you inject these technologies into bedrock. How do you install a slurry of solid materials into a bedrock formation?
Excellent question. So there's two methods of installing in a bedrock geology. We'll start with the most simple, and that's the competent geology, where you can drill a hole and it remains open. So we'll do steel surface casing through the overburden and into the competent bedrock and seal that into. So we'll cement that into the bedrock surface. And then we'll run an open borehole down to the total depth plus 10 feet, because what we'll run is we'll run a straddle packer string into there that can isolate an 18-inch interval. And once we get that 18-inch interval isolated, we can inject within the existing porosity and permeability of the fractures and features located within that specific interval that we're looking to target. If we're looking at a less competent form of bedrock, so if we talk about a section of vertical interval that will not remain open when you remove the tooling string and you can't put a packer in that, we have a method called geotap. And that tap stands for targeted access point. So geological targeted access point. And so these points are pre-drilled with some larger method using like air rotary, hollow stem auger, or sonic. And then we backfill that point with hydrated bentonite and lifts. And then we can basically go right back through that hydrated bentonite with a direct push unit, usually something as simple as a 7822 geoprobe, and inject right through the bentonite into the surrounding geology. So when you run into a situation where you can't probe it like you would an overburden, you drill it like bedrock and you inject it like it's overburdened using a combination of the two methods and the sealing of the borehole method.
All right. Well, that was a good question for you. I'll just mention to everybody that's still on with us here that Bill is certainly one of our experts when it comes to doing geophysical assessments of bedrock and helping come up with really effective plans to get the materials in contact with the contaminants after that assessment. We're at the top of the hour. I got one more question here. I think it'd be a great one to close out with. We can just steal another minute or two. What do you evaluate when you do a pilot test, and how long do you recommend the pilot test be in place before you are ready to move on to a final design?
Interesting question. And I think that can vary depending on the site. But when we do a pilot test, we're really wanting to look at verifying distribution and placement of the material. So it's going to focus on whatever method of installation is going to focus on a measurable point of assessment, that being physical and chemical. So we're going to look at hydraulic changes, colorimetric changes. You know, to say it's a monitoring well, for instance, or a piezometer we put in. Going to look at colorimetric changes in the water. Going to look at chemistry changes in the water, whether it's concentration or a contaminant or tracers, for instance, like the anions or components of the technology putting in there. And then looking at that time frame, I think it's going to vary based upon what the goals are and what the full scale design looks like. So, you know, part of that pilot could be to look at, you know, if we're just looking at a minimal amount or a suitable amount to assess, it could be looking at how long until depletion of those terminal electron acceptors in the case of this particular technology. So that could help fuel and make decisions as far as how we augment any sort of supplements and any sort of maintenance schedule that may come into play during full scale. So those are the kind of things that come out of that question right offhand without taking up too much time. But that's what comes to mind as I think.
Yeah. Oh, that's great. That's great. Okay. Well, that's the end of our questions here. So just want to thank everybody again for taking your time out. It's really a busy season for everybody in this industry. So we're very grateful that you spent some of your time with us today. I'll just mention that you know, he's got our website listed there on the screen. We do have a project evaluation form. You can go on there and upload documents, put in some particulars about your site, and we at no cost will review the information that you have and let you know if we believe that any of these technologies are viable for your site. Put together a preliminary design at no cost for you, just to you know, help you compare technologies and see what's best for you. Also, you can reach out to Bill. Bill, I don't see your email address. I don't know if that got clipped off there, but
yeah. Should be at the bottom, Ed. Can you see it down here, or is it cut off on the screen for everybody?
Maybe it's because I've got a little control panel thing blocking it. Yeah. Okay. Feel free to reach out to Bill at any time, or any of us through our website. Watch for a recording of this webinar to appear on our website. There's a lot of others there. If we've just touched on something that you're interested in, there's a great library. A lot of stuff can be learned there over that first cup of coffee in the morning when you're in the mood to learn some technical things. So hope you take advantage of that opportunity. Bill, I'll let you sign us off.
All right. Thanks, Ed. And of course, thanks everybody. I really appreciate your time during, you know, East Coast lunch hour here or any of the busier times of the work schedule. look forward to seeing everybody in person at events or on a future webinar. Again, feel free to visit our website listed here. And if you can't see my email address at the bottom, it's bbrab@astenb.com. You can find that contact info on the website if you would like to reach out to me directly. And with that, thank you, everyone. Enjoy the rest of your day, and we'll talk again soon.